this is how they are now, and they may be different 6 weeks later, so you can't call it like, oh, they have diastolic dysfunction yet, but you can say right now they are acting like they have diastolic dysfunction. So basically what we're worried about is we're giving fluids to these patients and our ventricle is stiff and it has high filling pressures, that in order to get that same preload where we'll just keep pumping fluids in and in and in, the left atrial pressures are going to get high because the ventricle's stiff, right? So it takes more pressure to fill it, and that's going to back up into the lungs, and that's going to cause mortality problems, okay? So we got a ventricle, heart here, RV, LV, right? We got mitral valves. This is an apical 4, right? Okay, so left ventricle, left atria. Maybe you guys know, maybe you don't, but there's pulmonary veins that are dumping from the lungs into the left atria there, right? So when we put the pulse wave Doppler and we gate it, we're going to gate it where the valves open, right? Remember they kind of flutter open like 1, 2 like this, and so the first thing that happens in the cycle. Okay, so this is systole. So what happens during diastole is the filling pressure of the heart of the atria gets higher than the filling pressure of the ventricle. And at that point, the valve is going to pop open and blood's going to fill. And that happens all the way up until will be some filling happening here, and then it will kind of slow down, and then the atrial kick will give that second little thing. That's why you get the valve going like this, right? The pressure differential between the left atria and the ventricle is what we're measuring with our first measurement here, okay? And what we're really kind of after is two things, is if the ventricle is relaxing fast enough, and we're worried about if the left atrial pressures are high, okay? The thing that makes the heart relax is basically just three things, okay? The first thing is how quickly the heart is able to let go of the little bonds that were made during systole. So remember there's the actin, the myosin, the troponin, and all that complex. And so when there's a lot of calcium in the cell, what happens is that all those things link up and squeeze, okay? And you have to get them to let go as a the kind of the first thing for the heart to be able to relax. And so how that happens is all the calcium in the blood that's making the whole complex bind has to get pumped out. Okay, so we'll pump it out of the cell or pump it into the like a compartment inside the cell. It's away from there, like a sarcolemma or sarcoplasm, and that burns ATP. So a sick heart that's not getting good blood supply and all that can't make as much ATP, and so it will affect how fast the heart can relax because you can't pump the ATP out of the cells. So that's the first thing is how fast can the heart relax, and that's ATP dependent. Okay. The second thing is think of the heart muscle as sort of like a sponge. Okay, and so if you have a sponge, you squeeze a sponge, right, and then you let go of it. It has its own kind of, springiness that kind of wants to come back to its original shape, okay? So there's this natural, desire to return to its relaxation state. How fast that happens depends on how much ATP is around and how healthy that heart is at relaxing quickly, okay? It's also kind of affected by, if there's some fibrosis or whatever in the heart too. So that's why old people always have relaxation abnormalities, is because it factors in there too. Okay, but that's the second one. So those first two factors are actually, if you think about it, making the ventricle pop open and suck things in. So it's a suction. Okay, and you can see how it's a suction because it's springing up, and how fast it springs up is how fast it sucks. Okay. The third thing that causes a pressure differential between the ventricle and the atria is what are the pressures inside the left atria. Okay? So, if we have let me just draw like a pressure volume loop to kind of explain here what's going on. So here's pressure, and here's volume, And so we have like the heart contracting, and it's going to have high pressures until it kind of peters out, equals aortic pressures, and then it's going to relax, and the volume is going to stay the same for a very brief amount of time. Okay, so we call this isovolemic relaxation. Okay, so we'll just do a little isovolemic relaxation. And then what happens is at some point the pressure inside the ventricle becomes less than the pressure inside the atria. And that might be because of suction, the suction being the primary thing, which is the healthy thing, or the unhealthy thing is a lot of push, okay, more push than suction, okay? But whatever it is, it's the ventricle will start to fill and our volume will go up. And at first we don't get much pressure built up, but eventually we kind of come to the limits of how much stretch the ventricle can do to accept the blood. And then it stops. And then what happens is we have the contraction happen, isovolemic contraction, and the cycle starts over again. Okay? So basically, what we're wanting to deal with is this little isovolemic relaxation time, and then this filling time here up until the point of isovolemic contraction. Okay? So this is the diastolic. Okay? And so when we put the gate here, okay, what we get is basically a pattern, and we'll start with a healthy heart. So first we get this little isovolemic relaxation time. Okay, guys don't need to pay too much attention to that, all right? But it should be around 70 to 90 milliseconds. Okay, it's very, very short. Okay, and then what happens is, as soon as this becomes negatively, like, the suction happens and a little bit of push happens here, we get the mitral valve popping open, and then we have filling of the ventricle, and then it rapidly fills. Okay, and then it actually starts to kind of get to the limits of it, and then it slows down the filling as the pressures start to equalize between these two things. And so we call this early filling, early passive filling. Okay, and then once it kind of peters out and comes almost back to the baseline where there's no flow going in between the two chambers, we call that diastasis, and it's relatively short. And we should talk about something real quick right here. This is called the deceleration time. And it should go from about 160 milliseconds to 240 milliseconds, okay? And I'll show you it's going to change over time. But then the final thing that happens during diastole is then the atria squeezes, right? And as the atria squeezes, the pressure in the atria, because it contracts, got a little higher than what's in the ventricle, because it's squeezed, because before they kind of like equalized as the filling slowed, right? And the valve kind of creeps back, and then it hits it again, and you get like another wave. And we call this the A wave for atrial kick. Okay?
If you have where you put the gate, does it matter a lot, or
you want to put the gate right where the tips of the valve is when it's during that early filling. Okay? That's where you want to put it. And you want to get a nice apical 4. Okay? Okay, so this should be taller than this, because there's, and remember, we're talking about pressure differentials driving this flow that we're measuring, right? This is actually flow we're talking about. And because of some physics, the velocities, the peak velocities of that flow tell you about pressure differentials in the chamber. And again, remember that this could have less pressure than this because it's negatively sucking, or because there's positive pushing, or anywhere in between. Okay, so suction, a little of both, or just push, mainly push. Okay, so this ratio normally should be less than 0.8. So let's just make it easy on everybody, and let's just say it should be greater than 1 and less than 2. The velocity ratio. Okay? Okay. So in a normal healthy heart, this pressure differential and this flow is driven by primarily a negative suction. Okay? What happens is that when we get diastolic dysfunction, and this happens in, if you guys see this, this will even happen in a 20-year-old female with pyelonephritis, is they'll develop diastolic dysfunction, okay, and their hearts get a little stiff, okay, and so what will happen is you'll get this isovolemic relaxation time. It'll be a little bit longer because the ventricle is kind of stiff, and so it just takes a few milliseconds longer to actually have this become less pressure than this, okay? And then the valve opens, and we get the E wave, but because the heart is stiff, it reaches that limit of the compliance faster. So the pressure differential isn't as high because we don't have this big lack of suction, okay? And then it just kind of still sort of rumbles on and keeps filling, but we have this longer deceleration time, more than 240 milliseconds. And so what happens is that we get when the pressures equalize, we still have a lot of volume left in the atria. Normally, here about 20% of the volume is in the atria at the time of contraction. Maybe 30%, 20-30%. But now maybe it's 35-40% that's left in the atria. So the atria contracts and it generates a higher pressure than what the passive filling was, because there's more volume in this pushes, okay? And so this is a relaxation abnormality, okay? What the paper you guys have does a grading system, like grade 1, 2, 3, and 4. Okay, the guidelines changed, and they grouped, they squished some of these and some of the next things into one called grade 2, and then they made the 3s and the 4s together in grade 3. And the reason why is because they just want to focus on if left atrial pressures are high or not. I think this is a little easier to. We'll talk about a little easier to remember, and we'll just skip grade 4, okay? But this when people talk about relaxation abnormalities, this is what they're talking about. Usually these pressures, these left atrial pressures, are still normal, okay? They can be high. The clues that it will be high if you see the atria and it looks kind of big to you. Or if you Doppler the tricuspid regurg and you see that they have pulmonary hypertension, the number is like 2.8 meters per second, would indicate that there's some pulmonary hypertension there. And then if you're dealing with diastolic dysfunction, you would assume some component of that is due to high left atrial pressures. Or this velocity is more than 50 centimeters per second. Okay, that would be some clues, but don't focus too much on it. When you see this, just call it a relaxation abnormality. Most of the time, left atrial pressures are still normal. Okay? Then what happens is the ventricle gets stiffer, even still. Okay? And so now we've kind of shifted to this point where the pressure differential between the ventricle and the atria is not because of negative suction, but now we've come into where the left atrial pressures are high, and now we're talking about more push than suck, okay? And so what happens is that it's still the same pressure differential, it's just where's the pressure differential coming from? Is it negatively generated here or positively generated here, okay? But what happens is that ventricle's stiff, and the relaxation time goes back to being short, because the left atrial pressures are higher, and they're going to get ready to get pushed and get to the pressure equalization faster. And then it opens up and comes back down to nearly normal pressures. This kind of, because it behaves the same way, because the pressure differential is basically the same sort of dynamics. It's just push instead of suck. And now you have, again, a lot of atrial volume, and the atria is still kind of strong, and the pressures that it has to overcome aren't huge because these are super high left atrial pressures. But you get something that looks identical when we're talking about the pulse wave Doppler of the transmitral flow, looking like exactly the same. But it's not. And the difference is, this is suction, this is atrial push. Ventricular suction, atrial push, normal left atrial pressures, high left atrial pressures. Okay? So, again, this one was the EA ratio is less than 1. Okay? Technically it's less than 0.8, but I think it's just easier to remember if the E is less than the A. And then again, we come back here and it's greater than 1, but less than 2. Okay? And then finally what happens, I'll just kind of have to come up here, but the ventricle gets very stiff. Okay? And so the left atrial pressures get very high, and so this pressure gets overran very quickly, so you get less than 70 milliseconds, so a very short isovolemic relaxation time. And you get a very tall, skinny E wave, less than 160. Okay, and you get this, and then the atria is big and full, and the atria's got thin walls, and the pressures inside the ventricle are really high at this point, and so it tries to squeeze, and it just barely generates a little pressure, extra pressure to fill the ventricle, and so it's not that the pressures aren't high, they're very high, but these pressures are very high too, and so you can't get much higher because the atria is such a sissy. Okay? So now basically we have a EA ratio that is greater than 2 to 1. Okay? So it's pretty easy to tell this from these, but it's hard to tell this from this, right? Because these are identical. And I think if you look at a lot of 2D echo, you guys can see it. So if you guys look at kind of look at how big the aorta is and that parasternal long, and how big the right ventricle is, and how big the left atria is, they all should be about 1/3, 1/3, 1/3. If that left atrial looks bigger than the right ventricle or than the aorta at that level, that's probably an enlarged atria. Or if you look at it and it just looks kind of big, just by your gestalt, I mean, you can measure, but it takes kind of more advanced skills to do that you guys probably don't want to learn how to do. But you can look at it and say, oh yeah, it's big. That's high left atrial pressures. The other thing is, acutely, technically, you could have high left atrial pressures and not have the atria had time to remodel and kind of blown out and stuff like that. Okay, but we got to have a way to do this versus this. Okay, so we could actually, if Doppler the pulmonary vein flow. Okay, and what happens with the pulmonary vein flow is, remember we talked about the hepatic flow, and we have the Doppler the hepatic vein. We get the S wave, the D wave, and the A wave, right? And as the right atrial pressures go high, this gets smaller and smaller and smaller, and eventually fuses with the A wave and reverses and makes it like a biphasic wave. Well, the pulmonary vein is just like the hepatic vein, but we're kind of looking at it upside down because the blood's going to us instead of away from us, like in the IPC. So we can look at so we call it, again, an S wave, a D wave, and an A wave. Okay, and we can see if this is getting smaller compared to that, or if this is getting too wide compared to how wide this A wave is. That we have high left atrial pressures and we're dealing with pseudo-normalization. But the problem is that this is a little bit challenging because it's in the far field and it's kind of hard to see sometimes because the ultrasound beam is kind of petering out and attenuating and stuff. So you really can only get this in maybe, 60% of the people. But who you can get it in almost everybody is you can do a trick called tissue Doppler. Okay? And so what you do is you just push the little TDI button and then pulse wave. And all that does is it changes the settings of what the Doppler is detecting. So what this is set to see is stuff without much amplitude in terms of the echoes, like stuff like water or blood. It's like very black. It assigns that because it's not getting a big strong signal back. But tissue has a big strong signal, so it's bright. Okay, lots of echo coming back. So high amplitude. It pays attention to high amplitude and filters out low amplitude signals. The other thing is that this is going pretty fast through. So, and this moves really slow. So it says, I want low velocities, not high velocities. So it filters out all the Doppler, shifts that are high velocity shifts and pays attention to low velocity shifts. So that's why it's called tissue Doppler, is because the Doppler settings are just so that it won't pay attention to blood, pay attention to tissues. Okay. So basically, you can measure this in two places. Okay. You can measure it in lots of places, but traditionally it's measured here or here, right at the mitral valve cusps where they come in. It's called the mitral annulus. Okay. And so you want it. This is called the septal annulus, and this is called the lateral annulus. Okay, and so what the current recommendations are telling you to do is to take samples from both and average them and use those numbers. This normal here, I'll just tell you, is like greater than 10 centimeters per second, and this is greater than about 8 centimeters per second. Okay. And the Doppler pattern that happens is basically like this. So the left ventricle is like these fibers that kind of spiral this way, and then they spiral the other way, and then there's some longitudinal spirals, fibers too. And so when the ventricle contracts, it kind of rings like this. And watch what happens if this is the mitral annulus back here. It's going to come up, right? As it contracts, and then as it relaxes, it comes down. Okay, so it first kind of when a squeeze, it comes up like this. Okay, and then you get a little bit of this, and then you get the mitral valve opening. You have this isovolemic relaxation time where it's at the baseline for a little bit, and then you get a dip as the mitral valve opens, and what that is the ventricle filling and the base of the heart dropping. Okay. And so we call this an E. This is called an S prime. We call this an E prime. Okay? And then we get a second little bump when the atria kicks and it bounces down again. And we call it an A prime. Okay? So basically, the E, like I said, should be more than 7 on the septal, more 10 on the lateral. Okay? And what happens is when we start to get a relaxation abnormality, because the heart is stiffer, the E kind of doesn't get dropped down so much, and the A gets a little bigger. Okay, so you guys can see that on the page there, the second one, right? And then with pseudonormalization, it gets even, a little bit even worse. And then with a restrictive pattern, it gets ridiculously small. Okay. Okay. So now the way you tell normal from pseudonormal is this E prime velocity normal or not? And is the E larger than the A or not? Okay? So when you have low velocities here, like less than 10 lateral, less than 8 septal, then and you have this here, then the left atrial pressures are probably higher dealing with pseudonormalization. Okay? Does that make sense to everybody? Okay, so next thing is talking about the EE ratios and how we can kind of see how bad the left atrial pressure elevations are. Okay, so this here we talked about, it's telling us something about the pressure between the two chambers, right? And it could be suction or it could be push. But the pressures inside the ventricle are less than the pressures inside the atria, right? So it has something to do with pressure, but unfortunately, it also has something to do with how fast this is moving up and down. And so, or how fast it's relaxing, the heart is relaxing is a better way to put it, a more precise way to say it. And so it's inversely proportional to how fast it relaxes. There's a name for it, it's called tau. It comes from like just calf measurements, okay? This here has nothing to do with, or very little to do with pressure differentials between the two ventricles, but it actually is inversely proportional to that same relaxation constant. Okay? So if we divide the E by the E prime, then we make that the reciprocal, and we basically have something that is proportional to the change in pressure only, because the relaxation constant cancels out. Okay? So an EE ratio less than 8 or so has got normal left atrial pressures. And an EE ratio more than, say, 12 or 14 or something like that has got high left atrial pressures, almost for sure. Okay? In between, it could be kind of either way. It's sort of a little gray zone. If you take, there's been studies done where they take, in the cath labs, they'll take the EE ratios and they'll take the cath measurements of the left ventricular filling pressures, okay, at end diastole, which is going to be the same as the left atrial pressures, okay, and they measure it in a whole bunch of people, and they get like, a relationship like this. And so you can kind of draw a line through it, right? And now we can talk about the actual pressures and the EE ratios telling us about the pressures and describe it in a linear relationship. Remember, a linear relationship is y equals mx plus b, right? So the y-intercept is here, so basically we have the pressure, the cath pressure, equals the EE ratio times the slope. The EE ratio is plus B times whatever the slope is, okay? So let's call it mx plus B, okay? So this is the x, this is the y, m is the slope, b is the y-intercept, right? Remember that from algebra, basic algebra, right? So if they're in normal sinus rhythm, you guys don't have to remember this much, but the m is 1.24, and only do the lateral annulus here, okay? 1.24, and the b-intercept is 1.9. And in sinus tach, which is most of your patients, it's really easy. It's 1.5 and 1.5. Okay? So, there's other things you can do to substitute for an E if there's in certain circumstances. So we can do things like, it's called propagation velocities. Again, we can look at it with the pulmonary vein flows. But I'm telling you, this is like the easiest thing to do, and it's pretty reliable. Okay, for that. So that's it. Okay. Now, why is it important? It's important because if we're sitting here and someone wants to give them fluids, they're gonna it's gonna cause the filling pressures to go up, right? Because we're forcing fluid into something that doesn't want to stretch. So that's going to make high pressures, and those high pressures are going to drive wet lungs, right? Because they're going to make the hydrostatic pressures in the pulmonary capillaries leaky. And remember that the wet lungs make stiff lungs, and wet stiff lungs kill our patients and make them stay on vents longer and all that stuff, right? So what we see is when we go from here, normal left atrial pressures, and we start filling it, this is going to get higher and higher and higher compared to this until we go to a pseudo-normal pattern. So ideally, if we see this happening here, and we have a relaxation